let's try an application problem in here. The formula for the amount A in a savings account compounded n times per year for t years at an interest rate of R and an initial deposit of P is, I'm sure you have seen this equation in a pre-calculus or college algebra class, is A equal to P times 1 plus R over N, the quantity raised to the power of N times T, where P is the amount of money deposited for a period of T years and the interest is calculated N times a year. Now show that for continuous compounding. What's the meaning continuous compounding? It means interest is calculated continuously. If n is the number of times the interest is calculated. Now for example, if the interest is calculated 6 monthly, then n equal to 2. Is that right? But if the interest is compounded continuously, what's the value of n? The value of n will be infinite. There will be infinite calculations every year. So, what we are required to find is the limit of this quantity when n goes to infinity. Show that that limit equal to p e to the power of rt. So, continuous compounding means n, the number of times the interest is calculated, is infinite. And the formula for continuous compounding is the limiting value of this A. You see, this gives you the amount A after t years if interest is calculated n times a year, where n is finite, no problem there. If interest is calculated 12 times a year at the end of every month, we can do that calculation there. Now the question is, what will be the value of A when n is infinite? That means n goes to infinity. So, then A will be limit n goes to infinity, P times 1 plus R over N, all raised to the power of nt. Now we need to find the value of this. Okay, now here we have a power that contains the variable. T is our variable, is that right? Interest is calculated with time. Now that means we need to make an approach here. What kind of approach? When the expression has a power that contains the variable, the best way to deal with is what? Take ln of both sides. We have A equal to this quantity. Therefore, we take ln of both sides and then proceed from there. All right, help me take the ln. It will give me ln A equal to limit n goes to infinity of ln of this quantity. There you go. So, ln A equal to limit n goes to infinity ln of this quantity. All right. Can you write this in a simplified form? ln of P times a quantity will be ln P plus ln of that quantity. ln A times B is ln A plus ln B. So, first of all, we simplify this as ln of P times this is ln P plus ln of 1 plus R over N to the power of NT. Okay, since P is a constant, we can take it out of the limit. You see, limit n goes to infinity does not apply to ln P because P does not contain n. So we can actually remove it from the limit and take only the limit of this quantity. So how does that become then? It'll become, you've got to read it like this. ln A equal to ln P plus, we just take it out of the limit, ln P plus limit n goes to infinity of this quantity, ln 1 plus r over n to the power of nt. Okay, let's go to the next page. And how do we deal with that limit? Well, ln, you know that ln of a to the power of x is x ln a. So it becomes now nt gets multiplied, it'll be nt ln 1 plus r over n. Now, look at the manipulation I'm now doing here. In order that we may evaluate this limit, n goes to infinity, since the direct substitution doesn't give you any meaningful limit, we got to see if L'Hopital's rule can be applied. Now, in order to use L'Hopital's rule, the expression has to be of the form f of x divided by g of x. And now, if you notice, our variable here is n. We want to find the limit when n goes to infinity. So that's the variable there. So instead of multiplying n on the denominator, I just divide it by 1 over n. Now, does it make a difference? We have n times t here. So that n from the numerator, I took it and put in the denominator as 1 over n. Remember, a 1 over n in the denominator is the same as an n on the numerator. This is just a manipulation for what? To bring it in the form f of x over g of x. So, nt ln r 1 plus r over n now becomes t times ln 1 plus r over n divided by 1 over n. In actual fact, there is no difference between these two. This 1 over n, the n goes up. But it serves us well now, because now this is of the form f of x over g of x. Alright, if you now replace n by infinity, what will happen? R over infinity will be infinity. Infinity plus 1 is infinity. ln infinity is infinity. Is that right? And the denominator is, well, okay. Now, this becomes 0 over 0, which is infinity. And therefore, the limit of f of x divided by g of x, because this is of the intermediate form, can be now written as derivative of the numerator times derivative of the denominator. Now, I want to warn you here, remember t is not a variable in this case. Why? Because we are looking for limit n goes to infinity. N is our variable. So t is not the variable. The number of years is going to remain. We're going to get the interest calculated for a given number of years when the interest is calculated continuously. So the variable here is n, not t. So we need to find d by dn, the derivative with respect to n of this quantity, not with respect to t. Therefore t is a constant there. Alright, what is d by dn of this quantity, since t is a constant? And remember again, the derivative of an ln quantity. Now I'm going to repeat that again. The derivative of an ln quantity is 1 over that quantity, 1 over this quantity, multiplied by derivative of this quantity. That means the derivative of this will contain 1 plus r over n on the denominator and the derivative of this quantity on the numerator. Alright, tell me, what is the derivative of 1 plus r over n with respect to n? Derivative of 1 is 0, the derivative of r over n with respect to n. Alright, anybody? That's actually an extra credit question. The derivative of a over x with respect to x is negative a over x squared. The derivative of r over n with respect to n is negative r over n squared. Therefore, the derivative of this quantity will be negative r over n squared divided by 1 plus r over n. And of course, this will be also on the numerator. Alright, that's the derivative of the numerator. What's the derivative of the denominator? D by dn of 1 over n is negative 1 over n squared. There you go. Alright, look at this again. The derivative of this is t times 1 over the quantity, 1 over r over n, times the derivative of 1 plus r over n is negative r over n squared. One more time. T is a constant, that will remain there, times 1 over this quantity is this, times the derivative of that quantity is this, divided by negative 1 over n squared. And if you notice there, this r can go and join here as r times t, and negative 1 over n squared and negative 1 over n squared can cancel. Alright, let's try it again. As I said, that r can go and join there. There you go. So you get, that will be RT over 1 plus R over n multiplied by negative 1 over n squared over that negative 1 over n squared. That will cancel, leaving us with this quantity. So the right hand side of the expression now has ln p. That will be ln p plus limit n goes to infinity of this quantity, RT over 1 plus R over n. Okay, what is the value of this limit? Now if you apply n equal to infinity, if you replace n by infinity, what is R over infinity? When infinity comes on the denominator, the value becomes 0. So when you replace n by infinity, this will become 0. Therefore, the limiting value of this will be RT. There you go. So that will be, on the right side, we get ln p plus the limiting value of this when n is replaced by infinity, that will become 0. So we get ln A equal to ln P plus RT. That's how you should read it. ln A equal to ln P plus RT. Or ln A minus ln P equal to RT. Alright, what's ln A minus ln P? Ln of A divided by P. There you go. Ln of A divided by P is RT. And now change the ln form to exponential form. If ln of A over P equal to RT, what is A over P? If ln x equal to y, then x equal to e to the power of y. If ln A over P equal to RT, then quantity A over P is e to the power of RT. There you go. So we get A over P equal to e to the power of RT, and that gives you A equal to P e to the power of RT. We have solved for A, and we got the expression for when interest is calculated continuously, the amount of money invested for a period of t years at an interest rate of R will be A equal to P e to the power of RT. Now this is a very interesting and an important type of problem. I want you to go back and maybe try this on your own, some of these steps. Alright? Okay, now try and do this on your own. Use L'Hopital's rule to find limit x approaches infinity, x sine 1 over x. I'll give you a clue. And the clue is, in order to use L'Hopital's rule, you must have the expression of the form f of x over g of x. and a direct substitution